Let's get started now, Chapter 7. Here we're talking about estimating parameters and determining sample sizes. Remember, parameters relate to a population, whereas statistics relate to a sample from that population. In 7.1 altogether, we're covering estimating a population proportion. The key concepts in 7.1. Here we're going to discuss methods for using a sample proportion to make an inference about the value of the corresponding population proportion. Remember, if we have a population of data, then our samples make up that population. So within 7.1, we'll go through point estimates. We'll talk about why a sample proportion, or p-hat, is the best point estimate of the population proportion, or just lowercase p. We'll also talk about confidence intervals, so we'll use a sample proportion to construct a confidence interval to then estimate the true value of a population proportion. And thirdly, we'll talk about sample size, so we should know how to find the sample size necessary to estimate a population proportion. As you could imagine, the larger the sample size, the more accurate it would represent the entire population, versus a very small sample from a population might not be a great estimate of the population proportion. So let's first define a point estimate. So a point estimate is a single value used to estimate a population parameter. For instance, the sample proportion, or p-hat, is the best point estimate, so the best single value of the population proportion, or just lowercase p. In this image here, if we have a distribution, it looks symmetric, it looks bell-shaped. We know in the middle here of our distribution, that will always be our mu, or our mean. The mu represents the entire population mean. So if we want to estimate a population mean, for example, we could take a sample from the population, and then the mean that represents just that sample is considered a point estimate. Okay, and it really depends on what sample we take from the population in order to tell how close this point estimate from a single sample is going to be and how it compares to the entire population mean, or the entire population proportion. This does sound similar to what we've seen before in Chapter 6. Okay, but this is the first time we're seeing this verbiage of point estimate. Now, we've also previously talked a lot about unbiased and biased estimators. So it turns out that getting a point estimate is intended to be an unbiased estimator. So more on this, if we use p-hat as the point estimate of lowercase p, where this is of the population and this is of the sample, this p-hat value is going to be unbiased, and it will be the most consistent of the estimators that could be used. For more of a reminder on unbiased estimators, this is a statistic that targets the value of the corresponding population parameter. It does so in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. Again, we've touched on this directly in 6.3, where our examples of unbiased estimators were the sample proportion, the sample variance, and the sample mean. The sample proportion, the sample variance, and the sample mean, those all targeted the true values of the population, so we can consider them unbiased estimators in how they're calculated. Whereas examples of biased estimators were the standard deviation, the range, and the median. Those were the main ones we talked about in Chapter 6. I put this refresher on here again, so recall that statistics are for samples and parameters are for populations. Again, remember the bigger picture here. So if we have a huge population of data, it's much easier to take samples from that population in order to estimate different values of a population. It's much more difficult to calculate entire parameters for entire populations. It's usually easier and more straightforward to get statistics of samples from that population. And in order to truly state that the sample statistics are representative, or they do target a full population, then those sample statistics need to be considered unbiased estimators. Okay, so coming back to Chapter 7 now, the statistic of p-hat does target the population proportion, or lowercase p. Let's go into an example now using Facebook. This is data that we've seen before. So a certain poll was taken in which 1,487 adults were surveyed, and 43% of them said they have a Facebook page. I think we looked at something similar about adults that have heard of Facebook. So 43% of them say they do have a Facebook page. Based on that result, find the best point estimate to the single value of the proportion of all adults who have a Facebook page. So this is the only information we're given in the question, and then we need to find the best point estimate of the proportion of all adults, or of the proportion of the whole population of adults. So here's the setup of our question again. Then for the solution, we can think through it this way. Because the sample proportion is the best point estimate of the population proportion, then we conclude that the best point estimate of P, which is for the entire population, is equivalent to 0.43. We don't have any other information from the question aside from this percentage here. And recall that a point estimate is a single value used to estimate a population parameter. When we're finding a point estimate, it's really imperative that we find the single value that can be most representative of an entire population. If a question asks us instead for the percentage of all adults who have a Facebook page, then we'd take this 0.43, convert that back into a percentage, so that's 43%. That's what's given to us in the problem already, right here. So what we're doing in this question is we're taking a sample of all adults where our sample size is 1,487. Amongst this sample, we have a certain percentage of adults that do have a Facebook page. That's 0.43 as far as probability. It's 43% as far as a percentage. We're being asked to take this information that's a sample of all adults and then apply it to the full population of adults. The only thing we can do is to assume that these 1,487 randomly selected adults are truly representative of the whole population of adults. So then considering that we need one single best point estimate, then that's 0.43. Okay, so this example is getting you to start thinking about how do we determine best point estimates. When we figure out what's in the question, what's provided for us, then we can go from there. This is a sample, then we're asked about the full population. 0.43 represents our sample. Okay, then we can consider that 0.43 is a true estimate of the whole population. Next, we're going to talk about confidence intervals. So confidence interval, sometimes abbreviated CI. A confidence interval, or also called an interval estimate, is a range or an interval of values used to estimate the true value of a population parameter. And again, confidence interval is sometimes abbreviated as capital C, capital I. Recall that if something is an interval, then we have some barrier here, some line here, and then this is considered a full interval. We're not talking about one single data point here in our distribution. We're talking about a full confidence interval. This does build on what we've seen before, looking at distributions like this that are bell-shaped, they're symmetric. These are 3 examples of some common confidence intervals. And we'll talk a lot more in 7.1, how to determine these confidence intervals and what do they really mean? What do we know if we know the confidence interval is 90%, for example? The next important terminology here is a confidence level, where a confidence level is the probability 1 minus alpha. I underline probability here because probability values always have to add up to exactly 1. So for example, if alpha is equal to 0.05, we take 1 minus 0.05 or 1 minus alpha, we get the confidence level is 0.95 then. If we converted that into a percentage, that's 95%. Now connecting confidence levels to confidence intervals that we just talked about on the last slide, if our confidence level is considered 95%, then we take that as a 95% probability that the confidence interval, or CI, actually does contain the population parameter. Remembering that repetition helps us get a better estimate, a better unbiased estimate. This all holds true, assuming that the estimation process is repeated a large number of times. Typically, the more times something is repeated, a calculation, an experiment, for example, the more accurate our answer gets. Confidence levels can also be called the degree of confidence or the confidence coefficient. Visualizing this now, if we have a point estimate, remember that's a single value from a sample that's intended to be representative of a whole population. If we have this point estimate here as one single point, then we have the width of this confidence interval here that goes some distance below the point estimate and some distance above the point estimate. This whole span here is our confidence interval, and then we have limits on the lower half of the confidence interval and then on the upper half of the confidence interval. We'll practice determining these, we'll practice calculating these within 7.1. Now here for confidence levels, we can take 1 minus alpha to find our confidence level of 95%, for example. Let's talk more about the relationship now between the confidence level and this notation alpha. So remember, we take 1 minus alpha to get the confidence level. Then in this table here, we have some of the most common confidence levels, and you've seen them here pictured in a previous slide. For example, if we're told that alpha is 0.1, taking 1 minus alpha is going to be 0.90. Converting 0.90 into a percentage then is 90%. We've seen this one here now, so when alpha is 0.05, the confidence level is 0.95, or in a percentage, that's 95%. The third example here is when alpha is equal to 0.01, we take 1 minus 0.01, we get 0.99. Putting 0.99 into a percentage is 99%. So if we know the confidence level, either in a numerical form or in a percentage, we can always know then the corresponding alpha value and vice versa. It happens that the confidence level of 95% is the value used most often, so this one here in the second row. Now I mentioned we talk more about confidence intervals. What do they mean? So let's touch on how do we interpret these. This is a really important point in 7.1. So we have to be careful to interpret confidence intervals correctly. We're going to go through some examples of the correct way to interpret and the wrong way to interpret. For example, let's use this range. So here's this p-value. It's above 0.405 and it's less than 0.455. Using the most common percentage here, the correct way we can say this is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion. So remember, we take a sample, we find the point estimate of it, then we have a width of the confidence interval that goes below the point estimate and above the point estimate. Then coming back here, we could say that we are 95% confident that this interval that we just talked about actually does contain the true value of the population proportion. This is remembering that this interval here from 0.405 to 0.455 is based on a sample. Remembering that we want to connect a sample to an entire population, then we can use terminology like this. Being 95% confident that our interval actually does contain the true value of the population proportion is pretty high. Okay, so let's talk about the wrong way to interpret this. So, for example, the wrong way to say this is that there's a 95% chance that the true value of p will fall between 0.405 and 0.455. We're not saying anything about chance here, so this is an incorrect way to interpret this. Another very wrong way to interpret these confidence intervals is to say 95% of sample proportions will fall between 0.405 and 0.455. Okay, so this is incorrect as well. Really what it comes back to is saying that we are 95% confident, or whatever percentage value is here. We are some percent confident that the interval that we figured out does contain our true value of the population proportion. Another part of thinking about confidence levels is to touch on the process success rate. Okay, so a confidence level of some percent, for example, a confidence level of 95% tells us that the process we are using should, in the long run, result in the confidence interval limits that do contain the true population proportion 95% of the time. For example, let's say we have confidence intervals from 20 different samples. Each of these lines here is one of our samples. Then we find a different interval, a different confidence interval for each one of these samples. Our true population proportion here in lowercase p, we're told that it's 0.5 here based on this visual. According to how we interpret this meaning of 95% confidence level, we can say that repeating the process of however we collected each of these samples in the long run will result in confidence interval limits that do contain the true population proportion, or 0.5, only 95% of the time. And I should say only 95% of the time, because that is a pretty high amount of confidence we can have here. How can we look at this and tell that amongst these 20 samples and these 20 different intervals, how do we know that represents 95% of the time that we are representing the true population proportion within each of our samples? Well, here we have 20 different samples, right? All represented by these lines here. Only one of those 20 different samples does not contain the true population proportion here, which is at 0.5. The fifth sample here that we collected, it does not contain the true population proportion. That's only one of the 20 that doesn't contain our true population proportion. So if we calculate that, 1 out of 20, that's where 0.05 comes in. 1 minus 0.05 is 0.95. Okay, so here we're connecting the definition of confidence levels to the process in which we're collecting sample data each time. There's quite a bit of new terminology here, so another example of this is a critical value. How we define a critical value is the number on the borderline separating sample statistics that are significantly high or low from those that are not significant. To picture this, for example, we have a distribution, it's symmetric, it's bell-shaped. Locating our critical values here, it's the number on the borderline separating sample statistics that are significantly high over here or low from all of these in the middle that are not significant. Not significant then would be all these values here between these borderlines here. You'll also notice that this alpha notation comes back again here in this visual. So now connecting this definition of a critical value to a sample distribution like this, then to the notation that describes a critical value, we say that the number z subscript alpha over 2 is a critical value that's a z-score with the property that it is at the border that separates an area of alpha over 2 in the right tail of the standard normal distribution. So we know how to find z-scores using table A2 and or using Excel. We've also heard of this before too. So the standard normal distribution curve means that what again? We have a mean of exactly 0 and a standard deviation of exactly 1. So specifically, a critical value here is the z-score that separates this area here, which is an area of alpha over 2, from the rest of our data. And notice that it is on this side, the right-hand side of our normal distribution. We will practice calculating these. It's similar to what we've seen before using our idea of how to calculate z-score, but now we're introducing also this terminology of alpha and alpha over 2. And we will talk more about this. We'll do an example. So in finding a critical value, we can say that the critical value z subscript alpha over 2 is what we want to find. It has to correspond to a 95% confidence level. So in solving this, the first thing we should do is connect this 95% confidence level to our corresponding alpha and then go from there. So a 95% confidence level, if we take that out of a percentage, that's 0.95. 1 minus 0.95 is equal to an alpha value of 0.05. Now that we know our alpha value, we can go on to the next step. So then we find our alpha over 2 here. So we take 0.05 divided by 2, that's 0.025. So we took our confidence level, then we found the corresponding alpha value, then we divide alpha by 2. Recognizing what alpha over 2 is important. So we just saw on the past normal distribution that the area on the right-hand side and the left-hand side is equivalent to alpha over 2. So in other words, we know that the shaded region here is alpha over 2. Therefore, the shaded region here is equivalent to 0.025. Because our distribution is symmetric, then this value of alpha over 2 being equivalent to 0.025 is also the same on this hand side of the normal distribution. But keep in mind the definition of a critical value. We want to look at this right-hand side of the normal distribution. So let's keep going with this. So in order to find z subscript alpha over 2, which is our definition, it's how we define a critical value, then we do so by noting that the cumulative area under the curve is equal to 1. It's equal to 1 because we have a normal distribution. Then to find this area here, that's 1 minus the area here, and we found that alpha over 2 to be 0.025. So 1 minus 0.025 is 0.9750. Now this should look similar to what we've seen before because we know our cumulative area from the left, but we want to find this borderline here that defines our critical value. Some assumptions we can make that are built into this is that we do have a standard normal distribution, right? So our mean is equal to 0 and our standard deviation value is equal to 1. Because we already have a standard normal distribution, then we can go to our table A2, find the corresponding area value of 0.9750, and then find that z-score. We can also do this using Excel. So if you need a refresher on how to use a given area value, a given mean, and a given standard deviation value in order to find this corresponding x value, let me know. Also see some past slides and past presentations. Okay, so as mentioned, we can use Excel or table A2 to find the cumulative area from the left is 0.9750. We find that that corresponds to a z-score or an x value of 1.96. Then let's connect this all back now. So for a 95% confidence level, it's told in our question, the critical value therefore is z subscript alpha over 2. That z subscript alpha over 2 is equivalent to 1.96. I recommend practicing this right now, so using either table A2 or Excel and verify that you do get a z-score of 1.96 given this corresponding area value, this corresponding area from the left value. Coming back again to a wrong way to interpret the meaning of a 95% confidence level, when we're finding the critical value or we're finding that z subscript alpha over 2, we're finding a z-score. When we're finding a critical z-score for a 95% confidence interval, we use a cumulative area from the left of 0.9750. We found that by taking this confidence interval, connecting that to an alpha value, taking alpha over 2, then finding that cumulative area from the left and how that corresponds to a z-score. The wrong way to take this is seeing this 95% confidence level and then thinking that you need to find the cumulative area from the left using an area of 0.95. Do not do that. Think through all the steps, find your alpha value, take it step by step. This is another way to visualize it. Again, here's our mean of 0, and because it's a standard normal distribution, we also have a z-score of 0 right here. We had our confidence level, we found the alpha value, alpha over 2, then we found this cumulative area from the left, then we found the corresponding z-score given this cumulative area from the left. Now, we don't have to do this every time necessarily if we're using a common critical value. So in the previous example, we saw that a 95% confidence level results in a critical value of z subscript alpha over 2 of 1.96. Given that a 95% confidence level is the most common, then we can also think of these other common critical values. So looking at this table, we have a confidence level of 95 that corresponds to an alpha value of 0.05. That corresponds to a critical value of 1.96. We just determined that, we just proved that. If we're dealing with a confidence level of 90% or 99%, these are also common critical values that you can either memorize or have handy when doing practice problems or during an exam. For example, 90%, that corresponds again to that alpha value of 0.1. If you went through the same process we just did, you would get a critical value of 1.645. In the same respect, with a confidence level of 99%, that corresponds to an alpha value of 0.01. If you went through that same process again, you would get a critical value of 2.575. Again, these are ones you can memorize and or have handy for you. You might not have to calculate this every single time, depending on the confidence level that we're interested in. It is important, though, to know how to do this calculation and how to go from a confidence level value to an alpha value to a critical value. More new terminology here, so we're introducing this new concept of a margin of error. You can start to see how we visualize it here to get an idea of what this margin of error really reflects. So let's formally define this. When data from a simple random sample are used to estimate an entire population proportion, or lowercase p, the difference between the sample proportion, or p hat, and the population proportion, or lowercase p, is somewhat of an error. It's pretty rare that we take a sample, we find the sample proportion, and it's directly equal to the population proportion. Usually it's not, and that's where we get this idea of margin of error. There is some notation here, so the maximum likely amount of that error is the margin of error, which is denoted by uppercase E. This uppercase E, this idea of margin of error, is the maximum likely amount of error. For example, if there's a probability of 1 minus alpha, let's use this one we've been using before, where alpha is equal to 0.05. Therefore, this is equal to 0.95. This probability value is equal to 0.95. Then what this margin of error idea is saying is that the difference between the sample proportion p hat and the population proportion, or p, is going to be this margin of error, or uppercase E, or less, right? Because this uppercase E here represents the maximum likely amount of error. So the error can be up to E, or it'll be less than E. Other terminology you might see is that this margin of error, or uppercase E, can also be called the maximum error of the estimate. There is a way to calculate this. We'll find this by multiplying the critical value, or Z subscript alpha over 2, and the estimated standard deviation of sample proportions. We'll talk more about this calculation. So I just read out how we calculate this to show you in a formula for how we calculate the margin of error, or E. We take capital E to be equal to the critical value, or Z subscript alpha over 2, multiplied by the square root of p hat times q hat over n. This part of the formula here is the estimated standard deviation of sample proportions. And then this value here you've seen now, so this is our critical value. For this estimated standard deviation of sample proportions, we're going to take p hat, which is the point estimate for the population proportion of successes, multiplied by q hat, which is the point estimate for the number of failures. Remember, this terminology of P and Q goes back to the binomial distribution section. And we're probably comfortable now with N, which is the number of sample values or trials. So for this part, we take P hat times Q hat divided by N, and then take the square root of that value. Then to ultimately find E, we take this critical value multiplied by all of this. We're going to talk more explicitly now about the different factors that go into confidence interval for estimating a population proportion, or lowercase p. Let's talk about why we do this. So the objective here is to construct a confidence interval used to estimate a population proportion p. Remember, we don't always want to take all the data from a whole population, so we can take a sample of that population and then see how that best estimates to our full population. This notation here you've seen throughout, so P is our population proportion. When it's labeled as P hat, that's our sample proportion. Then N, again, is the number of sample values or the number of trials. Capital E, now we've seen, that's our margin of error. Then Z, subscript alpha over 2, that's our critical value. It's also the Z-score that represents an area of alpha over 2 in the right tail of the standard normal distribution. Recall that for a standard normal distribution, our mean has to be equal to 0, our standard deviation has to be equal to 1. We have gone through previously how to take a non-standard normal distribution and how to treat it as a standard normal distribution. It's important to talk about when can we apply this. So there are some requirements here. Number 1 is that the sample is a simple random sample. It has to be an unbiased sample. It has to be taken randomly. Number 2, the conditions for the binomial distribution that we've seen before, we've talked about recently, are satisfied. Those are that there is a fixed number of trials. The trials are independent of one another. There are 2 categories, either a success or a failure, and the probabilities remain constant for each trial. For instance, the probability for the first trial has to remain the same for the probability for the 100th trial, for example. And this independent factor here means that what happens at the first trial has no influence on what would happen on the 100th trial. Number 3, there is at least 5 successes and at least 5 failures. Again, we need to have a larger data set we're dealing with in order to have more of an unbiased estimate of a sample to represent a whole population. So those are the requirements now. Now we'll go into confidence intervals and how to actually calculate that and notation for these. Remember, we're finding an interval. So we're not finding just one single point, we're finding a full interval here. So how we do this, how we find a confidence interval to estimate our population proportion, or lowercase p, is that we locate this population proportion p right here in the middle of this relationship. Then this value is always greater than p hat, which is the sample proportion minus our margin of error. On the other side of this, the population proportion here, P, is less than our sample proportion, P hat, plus our margin of error, E. So in this representation, we need to find our P hat value. We also need to calculate our margin of error, E, using this equation now that we've seen. So again, we want to think along the lines of an interval, right? So essentially what we're doing to find this confidence interval is often also expressed in this way. For example, we have our p hat, our sample proportion value, plus or minus our margin of error, E. You can also think of it like this. So here's our sample proportion p hat minus E, that would be on this side of the point estimate, to this side, which is our population proportion, or p hat, plus some margin of error. So in this visual, the estimate here is the p hat value. Then we subtract our margin of error, E, and we add our margin of error, E. Then this whole confidence interval spans this entire width here. Another detail to be aware of is for confidence interval estimates, there is a round off rule here. So you want to round the confidence interval limits for p to 3 significant digits. For example, 0.405, 0.455, these all have 3 sig figs, along with 2.92, 5.62, these also have 3 sig figs each. Okay, so we went through all these considerations. Now we're going to sum up all the procedural steps here. So number 1, verify that the requirements in the preceding slides are satisfied. In this slide deck, go back and look at slide number 22. Step number 2, use technology, so Excel or Table A2, to find the critical value that corresponds to Z subscript alpha over 2. In order to find this, you need to know your desired confidence level, then you find the corresponding alpha value, divide alpha by 2, then get 1 minus alpha over 2 to find the cumulative area from the left, then find that corresponding z-score that relates to that cumulative area from the left in a standard normal distribution. Step 3, we need to find capital E, our margin of error, using this equation here. Step 4, once we have our margin of error value and we also know our sample proportion value, or p hat, then we need to actually find the confidence interval limits by taking p hat minus our margin of error E and p hat plus E. Once we have p hat minus E and p hat plus E, we can substitute those values in the general format of the confidence interval. Bringing you back to this slide here, this is what's meant by this general format of a confidence interval, where we have our p-value here. We won't put anything in for our p-value, but now we can substitute in our p hat minus E and our p hat plus E value into this way of denoting this confidence interval. Then step number 5, not as significant of a step, but remember to round your resulting confidence interval limits to 3 significant digits. We're going to stop here for 7.1 part 1. Then in 7.1 part 2, we'll actually practice making these confidence intervals. So I will see you next time for 7.1 part 2. Let me know if you have any questions. Be sure to practice using table A2 or Excel. Practice along with me so you feel comfortable and ready for the exam days and for the cumulative final exam. I'll talk to you all soon.